Thank you, Matt. Great discussion. All right, everyone. It's the last session and last day of IGSS. And right off the bat, we have, sorry if I mispronounce your name, Gabriel Istrate.
Yeah, that's actually right. That's
very
good.
Okay. Okay, got it right. West University of Timisoara, Romania, and he'll be talking about taking agent-based model robustness seriously, some ways forward. And also, if you have any questions, as we've been doing, just raise your hand, and I will call on you at the end of the talk, or put it in the chat box, and I'll read it out. All right, over to you, Gabriel.
Okay, thank you. You see my screen, right?
Yes.
Okay, thank you. So thank you all for having me here. You might be wondering, who am I? I'm a theoretical computer scientist, and I'm actually fairly frequently proving theorems more than doing agent-based simulations. On the other hand, I do have a decent connection to agent-based modeling, and I did work in a past life at Los Alamos National Laboratory in the group of Chris Barrett and Mara Morate and Stephen Eubank. Now, of course, they're at University of Virginia, so people that were doing transients and episims. So I was involved and interested in agent-based modeling and the problem of verification and validation of social simulation. And this talk actually came by looking and watching the recording of Josh Epstein's talk, first at IGSS 2020. So there is some payoff for putting these things over the internet, and then at ASA 2020. And some of the things that I'm going to talk in this presentation are actually published in a paper that has appeared in AMAS 21. That's a typo. AMAS is this conference on sort of multi-agent systems, more on the software agent, but also there is some agent-based modeling. So what I'm going to do today is a combination of ideas, mostly from that paper, which it is going to read a little bit like a position paper, trying to tell you a couple of things I think we should do. And I'm going to present one technical tool that I've been developing called adversarial scheduling. So I'm going to concentrate on the idea, and I'm going to give only the overview of this one technical result. So what do I want to say? I want to say basically that if you want to solve this problem of verification and validation of agent-based modeling, and it's true also for things like mathematical models, we should basically develop logical frameworks for that. Of course, there are logical frameworks that should be tailored to the reality of social science and to agent-based modeling, so they shouldn't import directly the ones, but ultimately, I think that's the way to go. And I'm going to also discuss a couple of theoretical research directions associated with the point I'm trying to make. One about a proposed theory of robustness to primary changes and phase transitions in logical statements. So I'm talking about phase transition in logics. Okay, then a theory of adversarial perturbations and adversarial scheduling that I'm going to present is something that I've been doing. Actually, I've started thinking about this like in 2001 or so, but that's only one aspect. And I'm going to give some proposal on a couple of things that logics should, to be relevant for social scientists and ABM modelers, what they should be able to encode. So let's start with the problem that everyone at this workshop is interested. You have an ABM model, be it you built one or you learned one via some sort of inverse generative social science. Now what? Is the model credible? Is it true that you're going to get just, that the behavior of agents is very sensitive to small micro specification of the rules? And of course, as you probably everyone is familiar with. This is even more so important in a pandemic. So there was this paper, and I think I saw Flaminio Squazzoni was participated to this workshop, and a lot of other well-known people in the social simulation literature that had this manifesto in JAS about ways to, a call to action to create more robust models. But I would like to point out that the same problem is shared by people that do mathematical models. So, of course, the mathematician that just proved results about game theoretic models of agents on networks might not care that much about, okay, what he or she wants, what the model is about. It might just muddle along and that's it. But there is a debate, a significant debate in the literature on theoretical on the philosophy of economics, on the meaning of mathematical models in game theory and economics. So people have been calling, have been trying to figure out, okay, we have models, and of course they're incomplete. How do we interpret what the conclusions are? And people have proposed different roles for such models, from things like credible worlds, Sugden, to things like analogies, it's like Gilboa and other people. You can view them as parables or fables, a way to direct your thought. But they're also less, less cavalier interpretations. For instance, they were likened to children's toys. So essentially, they're made for the amusement of people and not that much more so. So whether you do game theoretic models mathematically or you do ABM, you sort of face similar problems. So if you want to solve this problem of, okay, is it typical, the run that you're getting, the system that you're getting, is it typical for an ensemble of models? Then you should probably solve the same problem in both situations. So I want to start by looking at some scenario where verification and validation is done, and it's important, and it's a multi-million-dollar industry, and it's a success of logic and formal methods. So nowadays we verify specifications of software that runs on airplanes and nuclear power plants and some other some other high performance software by logical and formal tools. And sort of the idea is that you specify your system properties in some version of temporal logic, linear temporal logic or continuous temporal logic. And then you also specify the property that you want to hold in the system. Something like the system is not stuck, or there is no configuration of events. Typically such such systems are distributed. They have many interacting parts, and sometimes these parts can update in unpredictable ways. So you want to write a specification that says that the system is not going to do something bad. And you translate that formula into a logical formula in this version of temporal logic. And then the theory of model checking, roughly speaking, what it does is it tries to find a scenario, an evolution path of the system that falsifies that formula. So it tries to create a combination of events where something bad happens. And the idea, of course, is that you want to eliminate that. So normally you don't want to have bad events happening. So you write a specification of the current model, of the current system, and you write a specification of the property that you want to satisfy. And you hope to find paths that are where something catastrophic happens, in the idea that you want to eliminate those. And this is, as I said, a multi-million-dollar industry. It has tools, it has versions that work on probabilistic models as well. And there are even more interesting versions of this idea, something called runtime verification, is the following idea. Again, you start with a logical specification of a property, of a system property, and that logical specification is automatically translated into a so-called monitor, which basically supervises the run of the system and automatically identifies the emergence of some interesting properties in the system run. So in a certain sense, it alerts you to something bad happening automatically. And these things are used all over the industry. So why don't we do something like this in agent-based modeling? Well, the answer is, on one hand, some people in the software agents literature are doing something like that. So if you look at conferences on computer science, conferences on software agents, you're going to see work on model checking agent systems, mostly for game theoretic agents, things like you want to check that auctions, for instance, have don't have undesirable properties. So something like that is done. On the other hand, of course, this is an approach that's not really popular within the ABM community, to the point that a very well-known people in the community have made the point that formal logic is not useful to designing multi-agent systems. And that's because people designing such logical systems tend to do armchair theorizing. So I actually believe that there is a role for logic, and sort of the misunderstanding comes from the fact that logic should be used for formal specification. You want to make clear what you're, what you're talking about, your concepts. You don't want to necessarily reason about those concepts. You just want to make them crisp and clear in a way that will be you can observe and maybe monitor from the simulation. And there is no need for inference, because on the other, you do have the simulation telling us what's going to happen. There is no need to do formal deduction, because you can just run the simulation and that's your deduction. Okay, so there are multiple questions to this point. The first one, a natural one, is how would the logic that would be useful for a social scientist and an ABM modeler look like? And I'm not going to tell you that at this moment. I'm going to just, of course, I don't really know it. I have some ideas, but on the other hand, I want to discuss, okay, suppose we have logic. Can logic talk in any way about ensembles of simulations? Can it talk about robustness of specified facts and things like that? Well, the answer is no and yes. On one hand, and now I'm putting my theoretical computer scientist hat. It's true that there is no place in logic, by and large these days, for the kind of continuous, for the kind of metricity that Josh was asking for. So you can't really have like a continuous family, a parameterized version of the same property as it changes for parameters. A proposition in a propositional logic is something, it's discrete. It's either this or that, and there is no continuum between that. However, there is work in theoretical computer science that points out that such methods might exist. And let's think a little bit about what would be an opposite of a robust statement, one which is robust under parameter change. Well, the notion would be a phase transition, right? We've probably all played with the NetLogo simulation, where you have a forest fire, and you adjust the tree density, and at some critical value, the properties of the burned forest changes totally, significantly compared to before. So in a way, we should, the opposite of a robust statement would be something that has a phase transition qualitatively. And it turns out that there is mathematics for random graphs for the Adversarial model in the area of final model theory, which actually talks about phase transitions in random graphs. And we do have some understanding of what makes a property of a graph to have or not have a phase transition. And roughly speaking, I'm translating here a precise mathematical statement. A property that has a phase transition is in a certain sense global. It depends on all the vertices and edges of the graph, not on a small neighborhood. For instance, having a triangle is local because you can just put a triangle on 3 edges, whereas having a Hamiltonian cycle is global. And there is a deep understanding of what kind of graph properties have phase transitions. And this is not limited to random graphs only. If you've been acquainted to the AI literature of the 90s, you know the work on phase transitions in random SAT. Well, I've actually worked on that, and we can actually, at this moment, we can characterize which versions of random satisfiability have a phase transition. So, on one hand, logic does not cannot talk about robustness. On the other hand, there are some results in logic and related fields that talk about phase transition in logical results. So I believe that something like this may exist for agent-based modeling, and that's like one proposal. Now, I said about, that I'm going to tell you something a little bit more technical than the statements that I've been making. So let me talk about adversarial scheduling. It's an approach that I've been developing for mathematical, that is game theoretic models, and I've published several papers on this one. And what am I doing in a nutshell? I'm replacing a model where agents activate at random with a model where I have agents activating according to a scheduler from an ensemble of schedulers. And I'm trying to identify properties of the scheduler that make a baseline result valid for the case of random update hold in general. Okay, so in a certain sense, I'm replacing the random scheduler to an ensemble of schedulers, and I'm proving, okay, suppose you have a scheduler from this class, then the following property will hold. And maybe normally the property won't necessarily be exactly the property that you're starting with, but some generalized version of it. So in a certain sense, I'm taking a mathematical result, and by generalizing it, I'm making it more, I'm getting a more robust version of it. In a way, I think that's responding mathematically, to kind of a question that Josh was asking ABM people to do. And I'm going to try to argue that one could probably do something like this for agent-based models as well. Of course, it's very limited evidence for that, but I'm going to come back to this idea that this is not only for mathematical models. Okay, and of course, this is something that, again, I guess everyone here knows. Update rule matters. So there were these great 90s results by Novak and May on one hand, and Berman and Glantz on the other one. So if you run spatial prisoner's dilemma, then the activation order matters. If you run it in parallel, like in a cellular automaton, then you get complex patterns. On the other hand, if you run it asynchronously, then uniformly at random, then the complexity that you get in the spatial case is not seen. So when I started thinking about adversarial scheduling in game theoretic models on networks, I thought, is there a single instance where a parallel or totally parallel or a random asynchronous activation order is socially plausible? Is there any social phenomenon that works like that? Frankly, I don't know. And most of the time, probably, for instance, random activation comes from our ignorance of the actual activation. And of course, the question is, are results crucially dependent on this assumption? That's the obvious question. So this was my motivating starting point. And what am I doing in a nutshell is the following. As I said, I'm taking some sort of finite agent models, some agents playing some game on a network, okay? Normally under random scheduling. And I understand that model mathematically, and I know that something happens, okay? Next, what do I do? I replace the random activation order by some sort of adversarial order where I am a daemon that can tell people, you activate. and I'm trying to break the baseline result by changing the activation order adversarially and keeping everything else the same. And I want to do that, and normally that's not very difficult. You can come up with a scheduling order where results don't hold. And the more interesting point is now you look at the proof of the mathematical result for the baseline case, and you look at what's happening for the adversarial schedule where things break. And by reverse engineering the proof of the baseline result, I'm attempting to figure out what property of the random scheduler actually was responsible for the baseline result to hold in that case. And doing this on mathematical models has very big advantages compared to social simulations, because I can just look at the proof and I can isolate basically the point where the proof would break, and what property of the random scheduler is used in the proof. Okay, the next step is I try to extend the baseline result by eliminating the bad scheduler. So instead of proving the result only for random scheduler, I'm trying to prove it for classes of schedulers that, of course, should eliminate that bad case. Okay, so that's the approach. I generalize the result, and I may do this multiple times. Okay, so that's the basic idea. Any questions so far? So here is my example for you. It's a mathematical version of Schelling segregation model. And the technical framework has the name of stochastic stability from evolution of game theory. It's due to Peyton Young. And the model itself was actually developed by Peyton Young in his book for the one-dimensional case. And there were some other people in the literature that looked at the model. Of course, I'm talking here about random scheduling, okay, for the 2D case. So I'm not taking something, a version of the Schelling model that I made up. I'm taking something that is basically resembling something from the literature. And the mathematical result of this analysis of Polycott and Weiss is informally that under random scheduling, the states that the system gets in are maximally segregated in the sense that there is a potential function which maximizes, which measures segregation, and these states, the limit states that are chosen, are the ones that maximize that potential function. And I do this, I'm going to just give you a flavor for the adversarial analysis, but the take-home message is the following. In such a model, if the scheduler cannot choose the pair that plays adaptively, that is depending on the actual system state, then basically the informal baseline result will extend. Okay, so as long as the scheduler cannot act on who's unhappy or who's more or less unhappy, but maybe act on, for instance, I was the last one to activate, maybe one of my friends will activate next, something like that. So that's not adaptive because it only deals with, it doesn't deal with my state. It does deal with who was the last to play, essentially. And as long as the scheduler is not adaptive in this sense, then the informal baseline result extends and the adaptive schedulers may break it. A couple of words about stochastic stability. This is in a book by Peyton Young, as I said. And the basic idea is that you might have a game theory dynamics, which has multiple equilibria, and they're path dependent. And the intuition that Peyton Young had was that you can actually select sometimes some of these equilibria by adding a small amount of noise and making the noise go to zero, and simply perturbing the actual dynamic that may lead to multiple equilibria will sometimes choose one equilibrium out of multiple ones. And he made the point that, for instance, perhaps things like the emergence of standards and norms, things like driving on the left or the right and choosing gold versus silver, could be modeled in some such game theoretic frameworks of stochastic stability. Now, this is the most horrible slide that I'm presenting, but to give you an intuition that what I'm doing is actually right. I'm taking a markup process P0, and that's the dynamic that may lead to multiple limit points in a in a path-dependent manner. And then I take a perturbed markup chain P epsilon, where P epsilon adds noise, parameterized by a noise rate epsilon. And I need some technical conditions on how this chain behaves. In a certain sense, it should converge nicely to the case without noise as the noise level goes to 0. And I look at the stationary distribution of this perturbed chain, which exists. Unlike the case of the unperturbed one, it may exist. And the state is a stochastically stable strategy if it has positive limit in the stationary distribution of this perturbed markup chain as the noise goes to 0. To some extent, the idea is like in simulated annealing, where you add a little bit of noise and that allows you to jump out of local minima. That's sort of the mathematical intuition behind it. Okay, so the model. I'm taking an n by n regular grid, rectangular grid with periodic boundary conditions, and I have two classes of agents, red or green, and I have some utility function on an agent, which depends on the number of agents having the same color and the number of agents having the opposite color. And you can tweak the parameters of this model to make it have maximum utility somewhere in the middle, not really at the end. So you're not necessarily wanting all the people to have the same color as you do have. Okay, and now for the random scheduling model, this is what Peyton Young and then Zhang did. You basically play like a Gibbs dynamics. You pick two random agents, and if they can improve their payoffs, they switch. Otherwise, they may switch with a small probability, which is like a Gibbs rule, inverse temperature, and you probably know the deal. Okay, so under random scheduling, the result that I told you that stochastically stable states are maximally segregated holds. Now, I took this model and I analyzed it where I put a general scheduler. And first of all, it's easy to break, and I'm going to tell you immediately. But let me tell you the model of a scheduler that's non-adaptive. And the idea is the following. I have for every edge that was last played, a probability distribution on the edges that can follow afterwards. Okay, so if edge E was played at moment I, then the edge played at the next moment is going to be sampled from this distribution that depends on the actual edge. And I need some version of weak reversibility in the sense that if edge E prime can be played immediately after E, then I can reverse the time. And of course, if you're familiar with Markov chain analysis, you probably know that something like this is needed, but it's not full reversibility. I'm not getting a product distribution or anything like that. So the next scheduled pair depends on the last scheduled pair, but not on the system state. And I do need a form of weak reversibility. And I proved that under Markovian asynchronous update, the version before, the stochastically stable state are essentially, now the Markov chain is no longer on the states of the system, but you need a state of the system plus the last edge. So it's already a slightly different result, but the components of the states of the system are still maximally segregated. So this is like the, like the original result, but in a more mathematically robust form, because I'm including here the random scheduler. It's basically like a complete graph. Every edge can follow after every other edge. And I can model by this the simplest form of contagion, where the next scheduled edge is based on the last, for instance, something like a friend of mine might decide to play with one of its neighbors, given that I was the one to play. So I can model something easy contagion like this. Okay, but if I let my schedule edge to depend on the actual state of the system, then I can easily create schedulers that forever precludes segregation. And all of this is mathematical. It's in a paper I published in 2018. Something similar can be done with multiple versions of models. For instance, one of them is strategic network formation, and Matt Jackson was actually introduced adaptive stochastic stability to such a framework, and there was work on in this direction, and you can probably adapt much of what I have done. Now, of course, this is all nice, but can you do something like this for agent-based models? Of course, I can't prove to you that I can, but let me give you a thought experiment, which you can map it to the most trivial ABM model possible in the form that there is no need for a simulation.
Gabriel?
So take the following, sorry.
Sorry, Gabriel. I think we might have to start wrapping up a bit.
Okay.
We're a little short on time. Yeah.
Oh, yeah, sorry.
All right, thank you.
Okay.
Sorry about that.
Okay. Let me then wrap up here, and thank everyone for the attention. And if you want to talk to me, please contact me. Thank you.
Okay, very interesting talk. I think we have time for a couple of questions. Let me look at the chat. We have Josh's hand up. Josh, do you want to go ahead?
Yeah, sure. Well, first of all, I'm very honored to be mentioned. I think this is a fascinating and very important line of work. For a long time, I've been worrying about the representation of agent-based models in logics of various sorts, and think this is just a very rich line of activity. The Pollacott and Weiss paper, I also think, is very seminal, understudied paper, very deep mathematical treatment of the Schelling model. On logics, I was wondering, Gabriel, whether, Erez Hatna and I have been working on this sort of problem, is that, deontic logic is an area that might be quite suitable to social science, in that you could think of ethical codes as a kind of inner product of deontic operators and possible actions. And for those of you who are not familiar with deontic logic, the operators are things like, it is permissible that, it is obligatory that, it is permissible to not do X, it is not permissible to do not X. All of these sorts of permissibility and obligatory ideas. They're intersubstitutable in some way, but in any event, one thought, Gabriel, is whether you thought deontic logic was an area that might be used to study the evolution of ethical codes and other things. The other one that I'm very interested in, and I thought, how much logical power do you put inside agents? I mean, do you allow agents to entertain contradictory propositions, or propositions that entail, P and not P, or that are unfalsifiable given data that's floating around? So two questions. Have you thought about deontic logic? Second, have you thought about endowing agents themselves with logic?
Yes, I thought about deontic logic. Frankly, it would be immodest for me to actually propose a logic, because I think that the proper way to do it would be to actually ask the community what is, and try to formalize what's important for them. So I'd rather, for me, logic here plays a very modest role. It's the role of, maybe you want to do everything, every kind of analysis in an automatic fashion on the computer. You want to specify what you're doing. For instance, you might want to formalize, say, the kind of robustness analysis that people have been doing in terms of variations of parameters and parameters search and things like that, and just have a middleware that will run that automatically, although almost to the point where you don't really look, you don't really eyeball what's going on at the data, and you do it automatically. So I don't see, logic as, it's basically for automation purposes, not for not for representing rich agents. Of course, you can do this with rich agents, but with very limited agents. So I don't believe, I mean, there is a role for rich agents, but frankly, if you want to scale at world scale, that's not going to happen. And it's debatable whether you need to. You know, I don't think you need to. I'm totally sold on the idea that, if we're going to get some sort of theory of social dynamics, it's mostly going to be like thermodynamics of computation, and you're not going to be able to predict or even validate an agent at the micro level. That's not going, I don't think, and given that, I don't think it's, you want to put too much into an agent. But so for me, logic would, at this point, would only do a service, try to automate, to make the kind of experiments that people are doing more systematic, and provide maybe the harnessing, so for instance, in terms of logic, I was going to say, for instance, that there is this work in analytic sociology about mechanisms. And one thing that I would love to be able to represent in a logic would be to represent what the kind of social mechanisms that sociologists like Hedstrom and others are talking about. Because, if you're going to develop a logic for logicians, you're not going to interest anyone. So you have to interact with social scientists. But other than that, it has to come essentially from the kind of couple of models that you would have to put up and basically tell the logic people what you would like. For instance, you might want to have things like statistical distributions in your logic. Of course, you might want to have some dynamic aspect because you want to represent change. So yeah, of course, deontic is, to my mind, is even one level higher than that, because you're talking about agents doing it. Whereas I'm only talking about logic as a way to, essentially automate what people are doing informally these days. And this is was even more so when doing transims and versions. You were running programs with shell scripts and all that. And if you were able to automate this and make it generate all those things automatically from specifications, that's what I'm looking at. That's what I'm shooting for.
Yeah.
Excellent. Very, very exciting discussion. I can see Rob's hand up as well. I think we're a little too much over time. Rob, if you would like to take your question offline with Gabriel.
Well, how about I just make one very brief point, is that model checking for multi-agent systems for ABMs has been around for a long time.
Yeah.
And in fact, NASA Langley has run conferences on this, Gabriel, for 20 years. And my sense is that
no, I'm well aware of that.
Yeah, and so I think as of like 10 years ago, I think the general idea was that for models of modest complexity, it's hard to do much practically with them. That was the rough summary of where all that went.
Well, things have scaled up nicely, and I happen to know I have foots in multiple communities. And for instance, Moshe Vardi is one person that has done tremendous contributions. And so things on the model checking side and runtime verification, for instance, side are much more scalable, are viewed as quite scalable in that community for mission critical ones. So I'm not proposing adapting those methods directly, because that's not the point. I mean, no one is going to care. No one cared at this moment. So you do have a point that those methods existed, and some people in the agent community, but not ABM community, are doing it, of course. And they've been doing it even recently, as I said, for things like verifying auction protocols and other kinds of voting methods and things like that. So I'm totally aware of that, because I'm more into that direction myself, in a certain sense.
Excellent. Great discussion. I think we might have some time during build session to continue. So without taking too much more time from the next speaker, we have